Hi, it's Adam Cankaya on June 1st, 2025, a couple weeks into the summer semester, and I'm just going to do a quick review of my status for this bladder cancer R project that I'm working on. This is a continuation from my last summer work that I'm hoping to finish it now and get it written up into a paper. So I've cleaned up all the code and I'll briefly go through it and then show you some of my early results and future plans. So there's several steps, 4 or 5 steps here. First step, of course, is to install all the libraries. I'm using mostly public libraries from the BIOC Manager project. Here is where I've enabled the multi-threading, and this is part of the speed improvements that I've done. For my, as I'm going to show you the results in a few minutes, my particular computer, the best results are with only 2 threads, but you can set whatever you want here to experiment. I experiment with up to 16, and it sounds like the overhead of the extra threads is not worth the computational improvement. So for my results, I'll show in a few minutes. 2 threads is the best. I'm saving my data to a local file so that I can load it quickly on the start. This will help speed it up. I have a timer that I'm starting, and these are just the queries to download the bladder cancer data from this database. I prepare it into a table, and yeah, so this is just the beginning, getting the data. This next step here is where I am looking for the differentially expressed genes. So I'm using this Lima pipeline here, where I go through this whole process to prepare the data, and then use this DGE list function to get a list of the genes, normalize it, filtering, um, and the result is this is the mean variance chart. You can see it's going down with the count, which is what I believe we want. So now we have all of the genes that are most differentially expressed from our original data. We now find the genes that are differentially expressed in either cases that are cancer or non-cancer. The genes are more common or less common, or I should say less or more expressed in either patients with cancer or without. That's the goal of this step, is to get that list of differentially expressed genes after filtering and other processing. So that's that step. Step 3 now is where we do some just visualizations of the DEGs. I'm making a volcano plot, heat map, scatter plot to show a rough geometric isolation of the tumor cases in this area, while everything else is here. This is the principal component analysis, so sort of shows that we're able to the most part, separate these cases from the non-tumor cases. And these are the heat maps showing some, it's a lot of information here, but it's showing the correlations between certain genes that are being expressed together. The real big thing I've done new here so far is the WGCNA that I've implemented. This is the um, gene network analysis, trying to make modules, putting genes into groups, and then treating them as one module and looking at how they are expressed or expressed less or more in certain patients. So that's what's this WGCNA step. This is brand new that I've done this summer. This is the step that takes the longest amount of time. There's several parameters that I calculate here, like this adjacency threshold parameter. Um, I've picked what I thought is the best one, And there's some other things here. This is where we actually run the WGCNA and try to save the results to a local file. These are some of this power. This is the soft power, block size. These are the two parameters that I want to do more testing on and to adjust to see if they influence the results. This block size is the number of genes, that maximum number of genes that can be put into a module. There's a minimum block size as well, and I should adjust these based upon the number of genes that I'm providing. And this is where I don't want to get too much into details right now, but we find the most significant modules, those most associated with tumors versus normal tissue. For my current results, this is module 3 and 5. And we do some calculations here. And these are the modules. You can see the log fold change. This is the amount of expression that we're using. So you can see module 3 has the highest positive log fold change, while module 5 has the most negative log fold change. The p-values here, they're very significant, -24, -22. These are some of the most common genes. And then this is another chart showing the cases are separated. These are normal and cancerous tissues. And then another thing now, I've made a Venn diagram that is trying to show the overlap between the DEGs and the module genes themselves. So let's see where it is. All right, I don't have the Venn diagram at the moment, but I have a Venn diagram showing the overlap between the negative and positive genes. And then this final step that I've now implemented is another step that takes a long time that I'm looking to improve. This is the actual gene set enrichment. So this is where we provide those modules. We say, all right, this module has this list of genes, and we try to annotate them to those genes to see how they're related to biological processes, cellular processes, those different molecular functions. So this is the initial results here. The results are okay, but they're kind of generic things. Like, as you can see, so these results are the most significant ones. As you can see, it's not very significant on I think these are the non-cancer patients. So this is why I need to adjust the parameters. Previously, those block size parameters, soft threshold, and then maybe some of these other parameters here, these things, to try to match the original paper's results, at least try to get some of the original functionality. And then here is where I actually do the print out the timing. So I will quickly show. So let's say the timer. Originally, with no multi-thread, just a single thread, it takes almost 1,000 seconds total, with half of that being the WGCNA step, and then a lot of it being this gene set analysis, enrichment analysis. There's some additional calculations that aren't necessary that I turn off, but the paper does make them for display purposes. If I do those, it takes much longer to run. But like, let's say the multi-thread, when I put 2 threads here, You'll see now it's gone down to less than 450 seconds compared to the original of almost 1,000. When I add more threads, like when I add 16 threads, it does not show an improvement. Actually, it's worse than the single thread. So, yeah. So that is a speed improvement that I've made with the multi-threading. And then, so I have a few next steps. The next step is to look at those parameter values, try to adjust them, try to match the original paper's values. I want to look at the other gene modules. Right now, I just looked at the top one of each up and down. Maybe I'll look at the top three, get some experiments, see maybe they provide some better enrichment results. And then I want to add some sort of AI component here. There are a lot of AI packages for R related to gene enrichment and gene set analysis. I need to look into my ability to add them. But as an example, there is this site from UCSD, GSAI. And what this is it's a website that you paste in a list of genes here, and it creates a natural language prompt, very complex prompt, that is then fed to a natural language LLM, language learning model. And then you get a result back of the functionality of those genes. So let's do a example here. So this is the result that's coming back. It's giving us, it's saying, all right, these three genes here are transcription factors related to cardiac development. These two are transcription factors for cardiac progenitor cells. So that's the idea, is that you paste in a list of genes, it tries to find commonalities amongst the genes, or otherwise tries to explain to you their biological role. There's all kinds of options here of different AI models. So there's two ways I can utilize this. This would be a replacement for this step here, and I could eliminate this step and just rely on this tool. So this tool, I could maybe use the website itself. I had found some R web scraper tools that you can use to literally load the page, put data into the form, get the response, and then something like that I could do. Or otherwise, this GSAI code is actually available, everything on GitHub, and I could potentially download it and run it on my machine. The only thing is I would need to sign up for the AI models, the web, like the Google engine, AI engine, ChatGPT engine. I would need to possibly pay for those, or at least sign up for the account. It's going to be quite a lot of work to manually get it running. If I wanted to spend all summer on this project, I could probably do that, but I most likely will just try to do the web scraping. So yeah, that's an idea for AI improvement. There are some other tools I may do. And then also I wanted to just try to take my code and share it with AI and ask the AI engines for suggestions of how to improve it, how to speed it up. I've read online that this is actually a common tactic now with AI. You can actually just share your code, and it will give you some suggestions for improvements. So that's where I currently am after a couple weeks this summer. I'm hoping to finish this up in the next couple weeks. I want to spend the rest of the summer on my System C work, but this is the current state.